We worked really hard in the previous video to establish that any continuous function whose domain is a compact set is automatically uniformly continuous. What's great about that result, among other things, is that uniformly continuous on a larger domain will guarantee uniform continuity on any subset of that larger domain. Right? If being delta close to x guarantees that I'm epsilon close to f of x on a larger subset of x values, then that will remain true on any smaller subset of x values. And so what this is going to let us do is demonstrate uniform continuity of a function on a domain which might not itself be compact, but can be expanded into a domain which is compact. So if I can take my function on a non-compact domain and extend it into a domain which is compact, and do so in a way that gives me a continuous extension into that compact domain, then that continuous extension will be uniformly continuous on that larger compact domain automatically, and that uniform continuity will then inherit to the original function on the smaller domain, even if that domain was not compact. I call this the continuous extension theorem. Let's take a look at an example of it in action. So here I have one of my favorite kinds of functions, which is one of these oscillating sine functions that tries to oscillate faster and faster as x gets closer to 0. So this is x times the sine of 1 over x. And I want to assess this function for uniform continuity on the domain which is the open interval from 0 to 1. Since it's an open interval from 0 to 1, the domain of this function is not compact. And so we don't automatically get uniform continuity. We can, however, check that this function is continuous at every point of this original domain. So what are our options? What could we try to do to demonstrate that this function is uniformly continuous on the open interval from 0 to 1? Well, when I look at this graph, I see that this graph has a lot of pretty nice properties, right? That it looks like it's really nicely well behaved on the entire open interval from 0 to 1. And also, the fact that 0 and 1 are themselves missing from my domain is giving me just these little open circles at the right end and the left end of my graph. And those open circles look like what we call in the business removable discontinuities. They look like holes that if we were to fill them in, we would still have a function which is continuous. And that bodes very well for our ability to demonstrate uniform continuity. So here's what we'll do. We will take our original function f and extend it in a continuous fashion to a function which is continuous on the larger domain which includes x equals 0 and it includes x equals 1. In other words, let's just fill in those holes. If I fill in the holes at the endpoint of the graph, which I can do because the limit of f as x approaches 0 from the right-hand side is nicely well defined. It exists. It's a finite real number. It happens to be 0 in this example. How do we know that it's 0? Well, that's an application of what we call in calculus the squeeze theorem, right? That x times the sine of 1 over x is squeezed in between plus and minus x, which both, as x approaches 0, have a limit of 0, and therefore the limit of x times the sine of 1 over x, which is in between them, also is 0, as x tends to 0. So essentially what we're saying is we can fill in that hole on the left side of the graph in a coherent way, in a continuous way that's coherent with the rest of the function in any neighborhood of x equals 0. And the same thing is also true at the right-hand endpoint. As we approach 1 from the left-hand side, f of x has a limit. That limit is a finite real number. It's called the sine of 1. Right? Just using the continuity of the function f of x equals x times the sine of 1 over x. We know it's continuous at least at every non-zero value of x. And so let's also fill in the hole on the right-hand side of this graph. And by filling in these two holes, we get a new function. If we then just sort of connect those holes with the same function in between as my original, I'm going to end up with a new function, which I'm going to call g. And this function is exactly the same as my original function f on the open interval from 0 to 1, but it also is defined at x equals 0 and x equals 1. It's defined at those endpoints where my original function was not. So this new function satisfies f equals g for all x's on my original open interval. But also, this function is a continuous function, not just on the open interval from 0 to 1, but it's also continuous at x equals 0 and at x equals 1 by construction. Because we filled in values for this g function, which were equal to the limits of the f function as x tended to 0 and as x tended to 1. So my new function is what we might call a continuous extension of f from the open interval from 0 to 1 into the closed interval from 0 to 1. And what's great about the closed interval from 0 to 1 is that it is a compact set. It's closed and it's bounded and it's a subset of the real numbers. So in the standard topology, it is a compact set. Therefore, by guarantee number 2, by the theorem that we worked so hard to prove in the previous video, we can conclude that g, my extension, is a uniformly continuous function on the closed interval from 0 to 1. Therefore, g is uniformly continuous on any subset of that closed interval. Again, because uniform continuity on a larger set guarantees uniform continuity on any smaller subset. And therefore, g is a uniformly continuous function on the open interval from 0 to 1. But on the open interval from 0 to 1, g and f are exactly the same function. Therefore, f is uniformly continuous on the open interval from 0 to 1. So this extension process gives us a really valuable way to prove that functions can be uniformly continuous even if their original domain was not compact in the first place. If I can extend my original function in a continuous fashion to a domain which is compact, for example, by filling in the missing values at the left and right hand endpoints, then we can guarantee that the original function was uniformly continuous on its original domain. This process, by the way, of taking a function which has some nice properties on some smaller subset and trying to extend it in a nice way, in a similarly nice way, beyond the boundaries of its original domain, this is something that analysts, people who study analysis, tend to do a lot. Right? And in some cases it's possible, in some cases they're kind of recipes for doing it. In some cases it might not always be possible to do. You might convince yourself, for example, that the reciprocal function on the open interval from 0 to 1 would not be nice enough to let us do this, right? We can't extend the function f of x equals 1 over x on the domain open interval 0 to 1 in a continuous fashion onto the closed interval from 0 to 1. We could fill in an open endpoint on the right-hand side, but because f doesn't have a limit on the left-hand side of that interval, we can't fill in a value on the x equals 0 that is going to make the extension of the reciprocal function continuous on the closed interval. So we can't deduce uniform continuity of the reciprocal function in the same way that we deduced uniform continuity of this example because we can't fill in both endpoints. And so a lot of times in analysis and in all of the sort of analysis adjacent disciplines, and this includes also things like geometry, this idea of extension, taking a nice thing on a small domain and extending it onto a similarly nice thing on a larger domain that agrees with my original thing, that's a big deal. It's a big sort of process. And this theorem is the first sort of taste of that kind of argument.